For this question, we have a rectangular profile with a base of length b and a height of length h, which is experiencing double shear. And the question is, if we were to come up with an equivalent or a substitute beam bending model, what length would that beam have such that the average stress would be half of the maximum bending stress? So let's review what double shear looks like. For double shear, we have two interfaces that are experiencing shear stress. And if you model a system like so, we could say that there is this green pin with a force from some type of plate coming this direction, and then there are going to be two plates on the opposite side that are going to be acting in the opposite direction on the pin, and the force of each of these plates is going to be half of the force of this plate on the left. The experiencing region, or the region experiencing shear, is given by these grayed out kind of pencil-like lines. And as we've described previously, if you get into this interface, what you would see is that it has an area and there's a shear stress that's acting on that area. So the area would be into the board, into the plane, and having the width in this direction that's given by the width across the pin. We can describe the average shear stress, and remember there are two of these interfaces, one up here and one down here. So the average shear stress across each of these interfaces is going to be the force. We could say this force divided by 2a, or we could say, oh, there's really F over 2 acting over this area. So we've established what the average shear stress might be. And let's think about how we might model this type of system as a beam with loading. And unlike question number one, the system that we're going to choose for beam bending is as follows. We have, in this case, a pin and a roller, so that might be this side and this side, with a force acting through or down this beam like you have here. This is an indeterminate, or this is a determinate system, not an indeterminate system. And the bending moment and the shear force diagrams can be solved purely through the use of equilibrium. The cross section of this beam, if we're, this is kind of exploded and, we're looking along the beam, would have a thickness h as described here, or a height h, and a base or a width b. The bending stress from the flexure formula can be given as sigma is equal to negative my over I. And for this problem, what we're doing is we're comparing the shear stress, okay, that we have in this system with double shear against the bending stress that we're going to have with this model here. And in order to calculate the bending stress, what we need to do is calculate the bending moment along the beam. And if you go back to notes and in prior efforts, what you would see here is that the bending moment along this beam going from left to right can be given as a triangle, and this is happening at L over 2. I guess I can mark that. Let's not get in the way there. So this is at L over 2, like that, and it maxes out at FL over 4. So if we're thinking about where is or what is the quantity of the maximum bending stress, we have to think, okay, I want the maximum bending moment, and that's happening halfway, so right underneath this force. The y is going to be the h over 2, okay, in this direction. And since this is positive, and this then becomes negative, actually we'll probably, if you want to think in terms of a positive quantity, you would actually pick the negative h over 2 going in this opposite direction. So you get negative times negative is going to be equal to positive, and the I is bh cubed over 12. That's the second moment of area, and we've just demonstrated how to calculate that out. So the maximum bending stress can be described as this bending moment, FL over 4, times the h over 2, that distance there, divided by the second moment of area, BH cubed over 12. And the question is, for what length L can we have this condition met where the average shear stress is equal to half of the maximum bending stress? I mean, we say, well, at what length L would the average shear stress be half the maximum bending stress? Okay, so this is how we make that condition. And again, similar to what we said in question 1, is that if the length is less than this, this quantity that we'll figure out, then the shear stress will dominate. And if L is larger than this, this equality is going to dictate, then we're going to have bending stress dominate, right? Because FL over 4 is the maximum bending moment, and as the length gets longer, this quantity FL over 4 gets longer. So we go ahead and we equate this equation right here with this equation right here. And we can do a little bit of algebra. We multiply both sides by h squared. You see that when we do that, we get an h on the left, and this is h over h cubed, so that would just give us a 1 on the right side. We can knock out the b's, we can knock out the f's, we can knock out the 2's, and if we look at the numerator here, we have L over 8, and then in the denominator, we'll just have 1 over 12. So H can be described as L over 8 on 1 over 12. And so L, to satisfy this equality right here, is equal to 2/3 H. Well, I hope you found this example interesting and helpful in terms of thinking about how the shear stress might dominate over bending stress when you have very small gaps between the applied loads in the case of double shear. And that those lengths being small would be when the length is less than 2/3 times the thickness of the beam, or if you could think of it as the thickness of this pin-like structure in the middle. Thank you.